Hi everyone, welcome to this video on calculations with strong acids and strong bases. Now this is the very last part of your note 17.3-1. This is Roman numeral 5 and 6. So Roman numeral 5 and 6 address this essential question. How do you calculate the pH from the concentration of a strong acid? Now it's a little bit different for a weak acid, and we'll get to that in the next set of notes. But for this one, we are going to calculate the pH from the concentration of strong acid. Now let's remind ourselves first, what is a strong acid? Well, strong acids, remember that they dissociate completely, right? As represented by the one-way arrow. Now when they dissociate completely, what we're saying is that all the available hydrogen ions are released into the solution as the hydronium ion. Let's take a look at, for example, as hydrochloric acid. So here I have hydrochloric acid, a common, well-known strong acid. It's part of the list of 6 acids that you need to know, so make sure to remember that hydrochloric acid is a strong acid. Now, because it's a strong acid, we know that it dissociates completely in water. So let's write the equation for that. Dissociate completely is your one-way arrow into H plus and Cl minus. Now, if you were to go into a lab and you take basically 1 liter, let's say, of hydrochloric acid of this concentration, about maybe 0.02. 0.2 of a molar for hydrochloric acid, you put this into water and it dissociates into hydrogen plus and chlorine minus. Now, you will find that if you analyze the concentration of each of these ions, you'll find that their concentration is the same thing as the concentration of hydrochloric acid. That means is after dissociation, this is the concentration of H plus, 0.2, and 0.2 is also the concentration of the chloride ion. Now, what does this mean then for us in terms of calculating pH? Remember that pH is the negative log of the concentration of H plus, right? Here's H plus. So if you already know the concentration of the acid, you know the concentration of the H plus. For strong acids, that is, right? There's a whole different set of things for a weak acid. So that's exactly the conclusion that came up with. If the concentration of the acid would equal to the concentration of your hydrogen ion. Let's go ahead and use this to apply it to an example problem. So let me erase that. And here I have an example problem. Can you calculate the pH of a solution of nitric acid of this concentration, 0.1 molar? It's always a good practice, right, to underline or just basically point out very clearly what is given to you and what is being asked of you in a word problem, so that it's easy for you to keep track of everything. So when you get your final answer, you're not confused by the numbers. So my pH is what I'm looking for. I'm going to put a little question mark indicating that, okay, I want to find a pH. Now I know that nitric acid is part of the 6 strong acids on our table. So strong acids dissociate completely into H plus and the anion. So let's go ahead and write down that chemical equation. Nitric acid, H plus, and the nitric ion. Now, because of this relationship, the concentration of the acid is equal to the concentration of the H plus ion. So, this is the concentration of the acid, 0.1 molar. If this is the concentration of the acid, then it's also the concentration of the H plus ion, and also the concentration of the nitric ion. So we want to find a pH, right? And the pH is, we know, is the negative log of the concentration of H plus. Here's H plus. Let's plug it in. So if you plug it in and you put it in your calculator correctly, you should get an answer of 1.0. Now at this point, I like for you to do this for all of your problems in this unit, acids and bases, is that make sure that your final numerical answer makes sense conceptually. This is what I mean. Nitric acid is a strong acid. So a strong acid, regardless of its concentration, whether it be very small like this, or maybe it's like, 6 molar or 12 molar, something like that, will probably have a pH in about 0 to 4 range, right, ballpark. or even lower than that, maybe 0 to 2. So if your pH, and somehow you calculate it to be like 13 or something like that, then you know that something's probably went wrong here. So you need to go back and check to see whether you missed a number somewhere, or maybe you punched in the calculator wrong. Right? Make sure to always check your final numerical answer so that it makes sense conceptually as well. Now let's take a look at a couple more example problems. This one, these you can do on your homework. These are all in your homework. And these two are a little bit different because they ask you for the pH and also the pOH. But remember that there's this relationship, pH plus pOH is equal to 14. So after you find the pH, using this number, the concentration of the acid, plug it in here, and find your pOH. Now let's take a look at a different type of problem using the same concept. So previously, you were given the concentration of the acid, and then you were asked to find the pH. This problem asks you for the concentration of the acid given the pH. So it asks for calculate the concentration of nitric acid needed to make a solution with a pH of 4.7. So I'm going to underline what's given to me, pH of 4.7. And then a question mark for whatever I'm trying to find. Now, remember that in order to find a concentration of pH, in order to find a concentration of the acid, we need to find a concentration of the hydrogen ion. And how can you find a hydrogen ion? From your pH. Because there's this relationship, right? The concentration of the hydrogen ion is equal to 10 to the power of negative pH. So, I'm going to have to plug this in. This turns out to be my concentration, or the numerical answer for my concentration of H+. Now, knowing that nitric acid is a strong acid, so the concentration of the strong acid is equal to the concentration of the hydrogen ion. Here's the hydrogen ion. So let's go ahead and rewrite that one more time to answer the question. So the concentration of nitric ion, that is 2.0 times 10 to the negative 5. Final answer. Now let's talk about bases. So we just talked about strong acids. Let's move on to bases. Here's a couple more example problems you do have in your notes, so you can take a look at that. So last Roman numeral of the notes is how to calculate make calculations with strong bases. As a reminder, strong bases work just like how strong acids work. They also dissociate completely into their respective ions. So for example, I have sodium hydroxide, typical strong base, right? It will dissociate completely into sodium plus and OH minus. Now the difference between a strong base and a strong acid is that a strong acid releases hydronium ion, or H+. A strong base releases the hydroxide ion. So all the available hydroxide ion, aka this one, are released into solution as this. There we go. Now, same thing as well with the strong acid for strong base. If you start out with 0.2 molar solution of sodium hydroxide, after it dissociates in water, you will find that the concentration of each of its ion is 0.2. So the same as the original strong base. 0.2, 0.2. So we came up with this conclusion. The concentration of the base is equal to the concentration of the hydroxide ion. Let's do an example to apply this relationship. Here, the example problems to ask you to calculate the pH of 0.1 molar sodium hydroxide. Now, sodium hydroxide, I just wrote the chemical equation, but let's rewrite it one more time. It's a strong base. It releases into sodium plus and OH minus. Now, the concentration of the hydroxide, of sodium hydroxide, is 0.1. So when it dissociates, the concentration of each of the ion is also 0.1. Now, this is where students go wrong, is this. They thought, oh hey, look, it's a strong base, I just need to take the negative log of that number and I'm done. But no, you're not. Because when you take the negative log of this number here, you are not finding the pH, you are finding the pOH. That's why it's always a good idea, right, to identify what's given, and then also make sure you know what it is that you're looking for. You're looking for the pH, not the pOH. Unless they ask for the pOH, then your answer would be correct. However, they're asking for the pH. But there is a nice relationship between a pOH and a pH that we can use. So let's do that. Now, at this point, let's go back to our problem. Let's calculate the pOH. So negative log of hydroxide ion giving me the pOH of 1. And then remember the relationship I just talked about a couple slides ago between pH and pOH? This one. pH plus pOH is equal to 14. So then the pH is 14 minus the pOH, giving me, plug this in, and here I have the final number. Make sure that your final number also has the correct amount of significant figure. Keeping in mind that number 14, because it's a constant, it has infinite sig fig. So, moral of the story is, do not just rely on taking a negative log of the first number you see. You need to make sure to read the question very carefully, identify what it is that they're given to you. So in this case, they're giving you a strong base, and what is it that they're asking of you? In this case, they're asking for the pH. So if they ask for the pH of a base, there's an extra step here. Now, if they ask for the pOH of a base, you're done here. Now, there is something interesting that happens with bases, and that has to do with the kind of bases that contains more than one hydroxide ion in the chemical formula. So it's this one, for example. So take a look at this compound, calcium hydroxide. There are 2 hydroxide per molecule. Now, because of this reason, your calculation changes a little bit. Calcium hydroxide is a strong base. So this is the chemical equation for its dissociation. It will break into calcium plus 2 and OH minus. But not just one OH minus, since there are 2 in the original molecule, when it breaks apart into its ions, there should also be 2 hydroxide ion. Now, the concentration of a strong base is still equal to the concentration of the hydroxide ion, but it's going to be equal to the total amount of the hydroxide ion in your solution. Since there are 2 hydroxide ion, you have to multiply the concentration by 2. So 1 hydroxide ion is 0.1 molar, just like before with sodium hydroxide, but because calcium hydroxide has 2 ion, you multiply that by 2, giving you 0.2 molar. That's how, this is 0.2 molar. So when you do your strong bases problem, make sure to, well, first identify your given in a question, but also make sure that you don't forget about the subscript, okay? If your strong bases have more than 1 hydroxide, be very careful of your calculation, because don't forget to multiply it by the appropriate subscript here. Now, that being said, we are at this part where we proceed as normal, meaning that let's go ahead and find the pOH. So let me erase this so we can see that. Okay, let's plug this number in to here, and then you should get this answer for your pOH. Now, this is also important to remember that you need to plug in your pOH with this new concentration here, not the 0.1, okay? Because your pOH is taking into account the concentration of all the hydroxide ion in the solution, not just one. So make sure you plug in the correct number here. Now, okay, well, we have this relationship again because they're asking for the pH. Let's do our arithmetic, and that should come out to be the pH of the strong base. Let's check to see if this final answer makes sense conceptually. So calcium hydroxide, a strong base, we expect it to fall, the pH to fall into the higher range, maybe 12 to 14, 13.30. I think that makes sense. So it seems to fall into the range that we expect it to be. So I think our answer is good. All right, so that's pretty much it for this set of notes. Go ahead and use this video, and also there's the video answer key for the worksheet on strong acids and bases. Use them as resources for you to complete them. And then thank you for your attention throughout this whole video, and I will see you in class. Bye-bye.